Yeah, thanks everybody for coming. It shows a certain amount of optimism on your part, being my third talk of the day and fourth talk of the conference, that you actually think I'm going to survive this one. and so I have to warn you, you'll recognize some of the slides because I couldn't count on everybody coming to the entire four-part series. But I've tried to make this different. So in this case, actually, what I'm doing is I said, oh yeah, that's right, I said this is going to be about fractals. And so I've got part of the Julia set here in the background. Is that part of the mandel? That might be, I think it's Julia. Anyway, I'm not going to get too heavily into the fractals. That can be a lot of fun to get into. But when I started off thinking, oh my goodness, I got to fill 4 tutorials now. I'll probably get into fractals, and I realize there's enough stuff without getting into that, and we're not using the fractal aspects of this all that much, and just the principles. But let me start off with the guy who kind of started this thing off, Fry Richardson. So is an interesting character. So he was the one that first asked, how long is the coast of Britain? And it's sort of interesting. Let me give you a little bit of a story here while you settle in, and then we'll see if there's any stragglers about why he got interested in that. He was a Quaker, and so he didn't go into the First World War. But prior to the First World War, actually, when he studied a whole bunch of different things. Really couldn't decide what he wanted to study, it seemed like. And then started working for the Weather Bureau in the UK, and was interested in problems of why can't we predict the weather. So, and he tried experiments like he'd take a whole bunch of ping pong balls and dump them into the river. They all start from about the same place at about the same time. Why do they get so dispersed? Or release a whole bunch of balloons from the same spot at the same time. And you go, how come they just don't all sort of go together? They get dispersed. So what's happening? So it was this notion of chaos started interesting him. World War I comes, and he says, I can't work for the government, I'm a Quaker. So he spends World War I in jail, according to the story I read. And then afterwards, he decides to get a PhD, I think, or he starts getting interested in psychology of deadly conflict. So why do people fight with each other? And so he needed to divide the world up into contiguous sort of groups that, and he was trying to figure out ways to do this. So when you divide the world up, there's all kinds of ways you could do it. So he needed some constraints, and one constraint was let's minimize the boundary area. So because we could gerrymander things and look like election districts in the United States, or we could try to make sort of nice sort of contiguous groups. So he was going for that. So he looked, and like Spain and Portugal gave different lengths for their common frontier. Well, how could that be? They're not having any border disputes, and why are they having different lengths for the common frontier? So then he got into sort of, well, how long is the coastline? And then I think he lost all track of his original question about why do people fight with each other, and got off on this thing. So the coastline problem. So as you try to measure the length of a squiggly line, and you get to smaller and smaller sort of line segments to do this, you follow it more and more faithfully, but you never ever get there, because as you follow it more and more faithfully, it's still little peninsulas and things that you haven't got yet. And so here's the scale, and as it gets smaller and smaller, you get more and more things, so it takes more and more length to do that. And so this is actually kind of a tricky problem, because if you want to get all the way around Britain, you can't start off with sort of any length, because then you end up with a gap, and how do you treat that gap? And right, so it's much easier actually to do this on a profile. And we kind of cheated here. It looks like they're all the same length. They're pretty close to all the same projected length, but you can actually have different projected lengths. So what we're doing here is the same thing Richardson did. How long is the profile? And we step along this. And I got interested in this in Switzerland because we're using RA, and I thought, why should RA correlate to anything? And I liked the fractal stuff because of all the pretty pictures, and I thought, how can I work this into my research? And I saw this paper that Underwood and Banerjee had written on some application of this, and I thought, I bet we could do that. We started off doing these calculations in Switzerland, and it would take all night for a group of computers to go through these calculations in 1985 or something, or 6, when we started doing this. But anyway, so what we see is we try to estimate the length of this line. The relative lengths go up and up. Step sizes, right, are getting smaller and smaller. And we can see we could still, fit more on there. And the relative length now goes from 1.09 to like 1.45. So we've picked up, something like 40% more length as we go to finer and finer scales. And this relates to the slope. So if we look at the relative length calculation that we just did, we can relate that to the slope in this way. And so it's a kind of weighted average of 1 over the cosine of the inclination of that segment. And here's the weighting factor, and it's pi, which is the projection of that one segment compared to the entire projection. And so what happens is this gets steeper, its weighting gets less, this gets bigger, so it stays well behaved according to L'Hopital's rule. And so this was the relative length. And then and let's see how that looks. So this was actually a measurement we made of a ski base with the UBM. So it's a series of profiles, and so we did profile calculations just like we just saw in this direction, and then we turned around and did them in this direction. And so this is the transverse, which is this magenta color here, and so we can see as we look at the relative length as a function of the scale of observation. At the longest lengths, it's 1, which means that the little line segments are not falling into these little grooves or climbing over the ridges in between them. They're just impervious to that. And then eventually they get small enough here so they start falling into some of those grooves and climbing out. And then they do it pretty consistently and start following this up and down. And so as you can easily imagine, if I look at the relative length in this direction, it's going to be different than it is in this direction because the ruler is going to tend to follow that, and they don't start picking up the roughness a little bit further out. So one of the things we're able to do is look at the anisotropy or directionality on the surface by comparing the length scale in the transverse to the longitudinal direction, because it's a highly directional kind of thing. And so we can see that on the ski base. Now, one of the interesting things, and as we saw in this morning's talk too, here's a 1 micrometer sampling interval measure of the ski base. You can see some measurement, what we assume to be measurement artifacts. Those lines aren't on the ski base, but it has to do with trying to hold the ski still while you move it on the stage. And so here we see, again, this is what we call the smooth rough crossover, where the line segments start falling in and climbing up. And one of the interesting things here is we get down to the finest scales. We can see the relative lengths are a bit longer than they were on the previous one. So we get down to these finer scales, and the longitudinal and transverse start to approach each other. And that's probably because we're picking up these measurement artifacts at that scale. And it could be that the geometries, as you zoom right into the 1 micrometer, there's 1 micrometer, this base starts looking kind of the same in both directions. You just got little torn bits of polyethylene that have been torn up by the high-speed grit that's coming by. So you can use this for looking at longitudinal, transverse, do directional things. We actually have a program called Tooth Fracs that steps around in a lot of different directions to try to see how anisotropic a surface can be, and that's been used to characterize teeth and tell the difference between what critters are eating by looking at which ones are most highly directional, and that we developed with Peter Unger and Rob Scott and the group at the other guys at Penn State and Johns Hopkins. Here's Mark Wahlberg, and I don't know if Mark's coming in this evening, but he's with Digital Metrology, and he was formerly with Cummins. And when he was at Cummins, Mark said, I have this problem. I'm looking at all these different instruments in Cummins. They make diesel engines, and we seem to be getting different results. So, and when we look at them all together, we're doing profiling. It looks like a big jumble if I'm looking at the FFTs. So here's the wavelength, and here's the amplitude. So we're looking at this, and this is all kind of jumbled together. I really can't tell what's going on. We're getting different measurements all over the factory, and we're trying to sort this out. So I said, Mark, we'll try a length scale and see how that works. This has already been sort of filtered to smooth it, so it's even worse before you do a moving average on it. And so here's the length scale, which is comparatively easy to see. And one of the things too we did here is we stopped making the calculation at the when we ran out of sampling interval. In other words, so the sampling interval on this instrument, these are all different instruments, the sampling interval on this instrument was much larger than it was, say, on this one. And so this is the same part measured on different profilers at different places in Cummins. And so we can see a large scatter, and we can see at what scale it really starts to scatter, about 10 micrometers. So, it's length scale can be a way of comparing instruments, and in this case, since it's a stylus, all we have is length to look at. So another thing that Mark did looking at this was he said, well, let's take an unfiltered profile and a filtered profile, and so it's a Gaussian 2.5 at 5%. So on a log scale, if we look at where 2 is on the log scale, somewhere in here, and so that so we can see now that the two length scale plots are diverging somewhere near where the Gaussian cutoff is, and we can see quite a dramatic effect on the Gaussian filter that the Gaussian filter has on the profile, looking at it in length scale. And we can see the same sorts of things when we use filters on area scale. The other thing that we can see, they measured it with a 2 micrometer radius, and then just using purely geometric simulation, not accounting for the fact that this is going to deform the surface less than this one if it has the same weight on it. But just looking at that, so you can see very clearly the effect of the stylus radius on a measurement. And so 2 versus 5, here's the linear scale. So somewhere between 1 and 10, we start seeing a divergence. So, sort of from a scale sense, that makes sense. So often when we look at these and we say, geez, well, where are we getting the changes? It seems to be near where you would expect it to be from some other kind of geometric analysis. So what we're seeing here is a scale-based decomposition of this measurement, and looking at the relative length at a whole bunch of different scales, and we can see how they look different. Now, so we started off with relative lengths, and then so how long is the coast of Britain? And then we got very clever and we said, maybe it works with area. And so there was this old joke that Vermont would be as big as Texas if you could flatten it out. So we decided, how big is the surface of Vermont, or how large is the surface of New England? But we started thinking about area too. Length, the path length, actually one of the fundamental things for path length we looked at, and was quite surprising, and maybe somebody here has some insight, and I'd love to work on this some more. Some initial tests show that the skin effect, when you look at very high frequency electrical signals, 20 gigahertz, they tend to travel on the outside of the conductor. Anybody familiar with this? All right, okay. Well, if you know of anybody that is, I'd like to talk about it. All right, so let's take a look at the importance of area. So area comes into a lot of these basic physics equations, Newton's law of cooling, mass transfer, charge transfer, load transfer, discrete interactions. And so I went into this in a little bit more detail before, but the key thing is here's an area term, and we're going to see in a moment that area changes with scale, just like length. So the question is, when I'm doing these equations, which area should I put in? Well, of course, they've been developed for the smooth area at some sort of human interaction scale. And so we account for the fact that the area varies with scale by this thing. So let's take a look at area varying with scale. So this has been in the U.S. patent, U.S. standard for a while. We had a patent, as I said, a while ago that's expired. This is the international standard that just came out, by the way. This did not, we tried to faithfully get the ASME ANSI one into this, and we didn't succeed. So I'm hoping we'll be able to modify this, because this is what people have been using in analysis, and this one missed it somehow. I'm not great at my ISO interactions, apparently. Anyway, so this is the same thing, except we tile with triangles this kind of way instead of measuring the length with a line segment. And this comes out to the same sort of relationship, except we get this little patch. Compared to that one is the weighted average, and the inclination, it's easier to figure it out from the angle to the normal to the surface. And so here's an example of relative areas on a surface. And as we go to finer and finer scales, we can see that the relative area goes up and the inclination, the average inclination goes up as well. And so we're calculating the inclination here, arc cosine of 1 over the relative area from that other equation. All right, so let's see how this works and some other examples. This morning I showed some different ones. This is mass transfer in fried foods. And we had Carolina Mero, who is a student in the Catholic University in Santiago in Chile. She'll be defending her dissertation in just a couple of weeks, and I'm going to go down there for that. But her question was, will the surface roughness influence the amount of oil that's transferred when I fry foods? Can I make fried foods healthier by having perhaps a smaller surface area? And as it turns out, that worked out. So, and we looked at these correlation tests. So this is based on relative area. And the question is, if I regress area at each scale as a function of the oil content in the fried food, will I see some sort of relationship? And here's an example of the two different things she was using, and I forget what these stand for. This is a gluten-based product, and this is whatever PF stands for. And so we got relative area versus the oil content, and so we can see that there is a positive relationship in both cases with the absorption of oil, which depends on the material, as you might expect. And so, so the theory here is that where we get the highest correlation, this is the actual scale of interaction. I'm not sure that's necessarily correctly identified there. Sometimes we see a much sharper peak. And but anyway, this has been published in the Journal of Food Engineering, and so you can look at that in more detail, from 2010. So. We have another example of mass transfer in carburization. So those are the two things we've done on mass transfer. We've done a few things with friction, and this is one of the neatest ones here. So this we're looking at the friction between a steel sheet and a milled die, and that's important because when you go into forming problems. You want to control the movement of the metal sheet in the die when you go to smush it and make like a car fender or something. So you want sort of more uniform thickness, and you don't want what you call orange peel effect on it. So controlling the movement of the metal in the die, if you can do that with the friction coefficient, which you should be able to, then you can improve your process. The problem is that nobody seems to know what this relationship should be. So what we did is we looked at 32 different characterization parameters to see which ones would be the best at correlating the friction and the texture. So it seems persuasive that the texture ought to be controlling the friction on these things to some degree at least. And the friction controls the flow. And so how do we figure out which texture characterization parameter to use? And we do this based on the ability to find correlations. So here's the basic method that I talked about earlier this morning in this particular embodiment. So manufacture different roughnesses. So there were 6 different kinds. Measure the surface. And this is the pin is what we're dragging these things over, and I'll show you how that looks in a moment. So the pin is the die surface. There stands for represents the die in this case. So then we characterize it with a bunch of different parameters, test the friction, and then do regression with all the texture characterization parameters. And the hypothesis is that, or the obvious thing is, we'll use the ones that do the best job of providing strong correlation. So here's the pin that's, and the surface is created by milling with 2 different feeds, coarse and a fine, rough and a fine. We get 6 different surfaces because we had 3 different materials. So 1 nodular cast iron, 2 different tool steels. So they were all machined with the same, the same program. Measurements were made with an interferometric microscope, a WICO, and there's the measurement conditions. And one of the interesting things is, there was only 2 machining conditions. Now, I wasn't involved in this part of the experimental design. And I would have been skeptical about this working out because you only got 2 machining conditions. Why don't you do some more? But with the 3 different materials, we can just look at this and say, oh yeah, we got 6 different surfaces there. And so here they are as measured. And then here too, so we removed the form as part of our process to evaluate these, which is normal. And so here we can see the coarse and the fine on pin 6. I don't know which material it is. Doesn't really matter. So here is the RMS or the SQ roughness. And there's the friction coefficient for these 2, just so you can see how that kind of lines up there. And so this one with the finer structure seems a little higher friction coefficient and a little higher SQ. So here are the parameters that we tried. So these are out of when this was a draft international standard a couple of years ago, and as I said, it just came out in print. So we tried this whole bunch here. Now some of these segmentation parameters, you can do pruning at different percentage. We just left it sort of at the default value because I was going to get too complicated. So a lot of these, you could have done more work changing the default values. All right, so here's what we tested, and these are the conventions of the normal height parameters. So we've got all 4 statistical moments or 3 statistical moments, height, valley, peak to valley, SA, okay. So this is what the setup looks like, but schematically, here's what happens, is you've got some back tension on this, and you just pull it over the tool. Sort of like you're drying yourself with a towel there, and you're measuring the force that it takes to do that. So here are the different friction coefficients, and here's the standard deviation of the friction coefficient. Now these were done in Neil Bai's lab in Denmark, and it's remarkable how low the standard deviations are in the friction coefficients. It's got a very small coefficient of variation. So they did a nice job there with that. So then we did the tiling exercise, and this is actually our example that we have in the standard, and it's not actually on those surfaces, but so as we get more patches at a finer scale, the relative area goes up and up. But as I said, that's not from this group. We just use that. So the relative areas we see here are a little bit smaller than they were in that example, but here are the 6 different colors and symbols for the 6 different pins. And so we can look at 2 things. We can look at the relative area here as a function of scale, like this, or we can take a look at the slope, and we call that the complexity. So at each scale, then we're going to do a regression of the friction versus the relative area, and also the complexity versus the, friction versus the relative area, the complexity versus the relative area at each scale, right? And calculate the correlation coefficient. And when we do that, we see that this seems to work pretty well. I didn't quite line those lines up right, but maximum R squared is about 0.9. So that means 90% of the variation in friction coefficient can be explained by the variation in relative area at that particular scale. So we can see at the large scales, this isn't doing much, and this is just kind of noise down here. Don't worry about that. But here, systematically, all of a sudden, we go to finer and finer scales. And this seems to work pretty well. So, wow, great. Good. So we've got a pretty good relationship here we could use to design dies, for example. If we look at the complexity, the interesting thing here is it works at a different scale, but even a higher R squared value. So that's just going to essentially the scale derivative of the relative area. When we look at all the other 25178 parameters, the ISO parameters, we note that these R-squareds are not too strong except for these two, the surface slope and the developed area. Well, it's not too surprising because the developed area is actually the same as the relative area, except it's only calculated at the finest scale, the scale of the sampling interval. So it looks very similar to what we calculated if we take this out. So if we go back here, for example. So that 0.72 would be around there, right? So it's not far off what we had. The algorithm for calculating that is slightly different. And then the slope, of course, we expect that to be similar, to have similar behavior because these two things, as we noted, are related. And in fact, all right, so if we look at the slopes on those two curves, so here's I'm not sure why it's a little different than what we reported, but all right, so it's about the same. Anyway, so there's the regression on on SDR, and then here's on SDQ. So the developed area and the slopes. So that's what those look like. Now, if we look at the developed area versus the relative area, we find these are very highly correlated. The relative area at the finest scale, which is where the developed area is calculated. So that this systematic difference that we see here is probably due to the algorithm that's used. And our algorithm keeps every tile exactly the same size to the precision of the computer as you tile over it. Whereas the algorithm that's used to calculate the developed area, I think, just goes from point to point. It doesn't worry about keeping the scale constant. It keeps the projected scale constant. We keep the actual tilted scale constant. So a little bit more complicated to do. Anyway, we look at the developed surface area versus the slope, RMS gradient, SDQ. We can see these two parameters are highly correlated, and that shouldn't be a surprise because you can't get more area without putting in steeper slopes. So in any event, all the parameters that correlate reasonably well, right, with friction are related to inclinations on the surface, and this is something too if you look at the literature. So, and it kind of makes sense. I've got an inclination, I'm trying to push something by it, and so that's sort of characterizing what's in the way. I got to get over these obstacles. So, and so all of these things seem to be related to the relative area. So here's our publication on this in the SERP Annals. Now, so here's another look at this. So the whole thing sort of made sense. Yeah, you get the relative area, you get the right scale. So the underlying theory is that there's two things that are important in characterizing the surface. Get the right kind of geometric feature, which seems to be area or slopes, and get the right size or the right scale. And if you do that, then you get a good correlation. So unfortunately, we didn't just stop there, because that makes a nice story. We get the right thing, it's the right area, right. So Johan was here from Sandvik and spent some time here, and Chaka Namsu Agawamba, who was here yesterday, is one of our students. He's actually from Massachusetts, but they kept their colorful Nigerian names when they moved here. And he was working on his master's degree in math. And so he did this sliding bandpass filter. And so we tried the whole thing in that. And for some reason, I was actually a co-author on this. I don't know. I must have dropped my own name from this for some reason. But okay. So anyway, here we are breaking this down into form, waviness, and roughness. But namsu is what we call them. Broke it down even more. So first you saw that roughness parameter analysis. Now we're using a series of bandpass filters together with the roughness parameters. This you've already seen. And so we use remove the form, level, and no other filtering. And then and then we calculate. Then we do these bandpass filters. So we take, it's a combination of a low pass and a high pass, so you're left with a band. And then we tried 3 different band widths because it wasn't clear how big the band should be, right? So, let's try several different things. The computer's doing the work. The center wavelengths, we'll go over the range of scales that essentially we had available in the measurement, and so it ends up being 50 filters as you step along. We call it sliding filter, but actually steps along, right? So, and then we'll do the linear regression, scale-sensitive fractal analysis. We already saw that. And so here's the amazing thing. Now, I've been spending a lot of the time in the last 2 days saying bad things about average roughness and what a worthless parameter this is because it jumbles everything together and basically because it's insensitive to scale. The interesting thing here is if I use the sliding bandpass filter and I get just the right scale, which is way down here at the fine end, I get a very good correlation coefficient. It actually beats the relative area. So, the thing is, of those 2 things, let's get the right character to the geometry, and let's get the right scale. It seems that getting the right scale is more important. And a number of different parameters will characterize the geometry. So that's kind of what we seem to take from that. We can see that the different bandwidths have got different behaviors. So there's the 3 different bandwidths. And when we use the 20, we get a very narrow peak. The interesting thing is we ran out of resolution in the measurement before we were sure that we got a peak on the 100. But still, nobody's complaining here, an R squared of 0.94 using average roughness. But the thing is, the average roughness, if I just do SA without doing the bandpass filter, it is most sensitive to the large scale. Some of you will remember my example with the sine wave, and when I add sort of high frequencies to low frequencies, the RA just keeps picking up the longer wavelengths, and is insensitive to the shorter wavelengths. So I can learn a lot more if I do a multi-scale analysis. And here were the other winners. Look at this. SA 0.94, 0.93, 0.92. So a whole bunch of different parameters seem to work well if we have the right wavelengths, and some of them work in slightly different wavelengths or scales. So for multi-scale analysis, this is really quite revealing. Not all of them were that good, but those were the best ones. And as I said, they beat the relative area, much to my embarrassment. There we go. So getting the right filter makes all the difference, and so the bandpass filters seem to work very well. Now, Chuka-Namsu Agawamba is still working on that. It still is a finicky program that's best used by Chuka-Namsu himself, but he's trying to get this to a more universal thing, and would be delighted for help and interest. And I don't know where he is today, but he was here yesterday. So the other thing is scale-sensitive fractal analysis, and then wavelets, which we didn't get to hear so much about because Hassan wasn't able to make it, would be another approach to this. So this was published in Scanning in the special issue that went along with the first international conference on surface metrology. All right, so we've looked at length scale and area scale. Here's what we initially called volume scale, but then ISO decided to use volume scale for something else, and having difficulties dealing with ISO, we decided we might call this filling scale, but you may hear me call it volume scale as well. And this is, we're using this on diamond wheel dressing. So this is a diamond wheel. This is a grinding wheel. And so you bring these two together with some skidding, and you break up the surface of the grinding wheel so that it's going to grind better. And so there's sort of where the two things come together. This is a device that's made by Bob Hahn, who's who came to these conferences when we first started doing these and celebrated his 90th birthday at one of them. So anyway, one of the interesting things, we start doing material removal tests in this with the diamond wheel dressing, and we change the the force per length, is where they come together. So we look at a length rather than an area. We can see there's like a kink in this curve, and so the question was, can we see some change in the surfaces? So after we did all these sort of material removal tests with Bob Hahn's special grinding machine, which you can see in one of our adjacent buildings, if you like, in the manufacturing labs. We haven't used it for a little while, but if anyone would like to have a look at it, they can. Anyway, so then we did surface measurements, detailed surface measurements of these, and said, can we tell, see if there's something different going on the surface? Now, one of the things that makes the surface on this tends to hide the differences in the surface. You think, well, you go in, and these are different dressing rates, right? So I've got the grinding wheel, I got the dressing wheel going, and I push them together, and you develop a certain force, and the material starts coming off the grinding wheel. And then, so you maybe have a nice surface on the grinding wheel. Now you have to pull them apart. And since they're elastic, they don't come apart instantaneously, and you wouldn't want them to anyway, because I'm like taking a circular shape out of another circle, and if I took them apart instantaneously, I'd have a big bump in it. So I've got to take them apart slowly, so I get that bump out of there. And then, and so as I take them apart slowly, I go from this sort of high aggressive grinding that might get me just the surface I wanted. So as I detract, I have to come apart gradually. So I mess up the surface. So the surface, I'm sort of wearing the surface as I bring them apart. So we measured these things on the scanning laser microscope, and I'd like to acknowledge Solaris Development's support for this. It's the old UBM that was made in Germany some time ago, and they imported. So we used replicas, and here's a measurement of a couple of the replicas. And the reason we're using replicas is we didn't want to have to take the wheel off and rebalance it every time, and so we thought that would mess up the results. So so we've inverted the replica, so you can see this is what the wheel looks like, right? Because the replica would be a negative, so we just inverted it in the machine. So here's the in the computer. So here is the less aggressive. Here's the most aggressive, and you kind of think you can see a difference there. And so here is another impression of these two. Here, if we put them all together, look at relative area versus scale, they're not sorting out very well. If we just look at the two, 800 versus 500, yeah, all right, so it looks like there's a bigger relative area in the 800, but there's still some overlap all the way through. And so this might be, as we're pulling them apart. If we do the F-test on this, the 800 versus the 500 are micrometers or 0.8 millimeters. Anyway, so we look at our biggest difference. We do, yep, they are, and as I said, I switched, as I said in the morning. We now call this discriminatable, so nobody thinks we're doing calculus and calling it differentiable. But all right, so here's the range, and I forgot what our certainty was on this. So this is the critical mean square ratio for something, and so this is a little bit troubling. This might be only 90%. So they were differentiable, but not over a very wide range. Anyway, so we went in to look at, let's see, mean relative area for each feed. Okay, so here they are looking at the means. Of course, just the means by themselves don't tell you much. You need to look at the variance, but we can tell the two middle ones are almost right on top of each other. Is that the two middle? No, it's not even the two middle ones. So the order is even out of whack. 0.5, 4, 8, 1.5. So we can tell right away we're not going to do a good job correlating with this, right? So it's a grinding wheel, though, and it's not just the area scale that's important. Well, that would give the inclination something about the cutting. The grinding wheel has got to transport chips out of the grinding zone, and it does this in the volume. and that's available, or in the filling sort of volume that's available. So we developed this filling scale analysis. We actually developed this for NASA for looking at runways, because the way you measure a runway texture or pavement texture currently is you take a known volume of carefully graded sand, dump it onto the runway, and then you got to spread it around. And the standard, the ASTM standard, describes the spreader that you use as a cylinder this thick, this diameter, made of hard rubber with a chamfer like this or a rounding on the edges like this. So it goes into a precise description of this, and then it has in parentheses afterwards, hockey puck. And so the neat thing about this is that it gives you a scale. In other words, the diameter of the hockey puck is it gives a scale to sort of conform to the road, and the size of the sand, there's scale on that too. Turns out that this does a pretty good job correlating with that. I didn't put that slide in here, but anyway, so as we look at the volume fraction, how much we're able to fill as a function of scale, here's the relationship there. And so this looks different. And then if we do the F-test for all the feed rate pairs, it looks like we're doing a pretty good job of discriminating based on the filling, on the fraction filled. And then if we go and take a look at the correlations, feed rate and volume fraction, this actually looks pretty good. We're getting pretty high correlations. So then, I'm going to sit down for a moment. So then, when we look at, geez, how is the, how do these correlation coefficients look overall? We have a little bit different pattern than we've seen before. And here's the points or the lines that we were looking at on the previous graph. But it does seem to have a tendency to go up. I'm not sure why we have all these ups and downs. And here it seems to be pretty solidly up. So this is, we were working with this filling scale for a while. It's still in the software. And there's different things you can do with it. You can do fraction filled or average texture depth, which is actually what that sand patch test does. So there's other things that seem like it would be good to know the volume of the surface for. And let me just go back to this, because this question had come up earlier today. So if we're looking at a plateau honed surface, let's say, and we're interested in is it relatively flat, and I should have an example of this here and I don't, but imagine it's relatively flat with some pockets in it that are supposed to hold wear debris and oil. And the question would be, how good is the surface going to be at that? Well, if the pocket is too big, the oil will all come out or the debris won't stay in there or something, so it wouldn't be good. So the hypothesis is we could do a better job of telling which surfaces might be good for bearing kinds of things, lubricated bearing applications, if we do the filling scale analysis as compared to the Abbott Firestone. The Abbott Firestone just looks at the amount of material versus the amount of voids, but it doesn't show how the voids are divided up. So it's a conventional parameter that once again misses some aspect of the scale. So clearly the scale here is important in finding this relationship. So filling is another way to look at the scale. So here's Bob Hahn. He was coming in 1 or 2 times a week until he was 90, working with us on his machine. So thanks to Bob Hahn and Saint-Gobain. All right, so we've looked at our original progression was length scale to area scale and to volume scale. And we've been most successful in finding correlations and applications for area scale. So length scale, area scale, volume scale. And we haven't tried a lot on the volume scale. That was developed originally for NASA and looking at runways. And that's the best correlation that we found that I just showed you with the grinding wheel dressing. And we'd always been interested in radius, and we knew that the radius on the surface would change with scale. And we know that slope is kind of encompassed in the area, although slope has got direction and orientation to it as well. And so there's obviously more potential to develop that. And then these guys, Professor C and his graduate student, I forget what his first name is, Moore, we're looking at cutting, and this is a biopsy needle, and so how well does this cut? So this you got a chunk push into you. It takes a chunk of tissue out. The tip of the biopsy needle is a flat sort of plane that's taken off. If it's a hypodermic needle, there's actually two parts to it. The hypodermic needle has the job of ripping your skin apart as it goes in, so that it doesn't fill with skin as it goes into you. And you want the biopsy needle to fill with the tissue. So they've got two different kinds of tips on them. Now the concern here was when you go in and take a biopsy, you don't want to disrupt the surrounding tissue any more than you have to. And these are often taken in rather unpleasant kinds of places where you'd rather not be poked with something. And so the idea is, let's try to see how pain-free and easy we can make this by making this sort of edge better. And so these guys did a presentation at the North American Manufacturing Research Conference, and they talked about the radius of this. And I got thinking about the radius again, because we'd always thought we'd like to measure radius. And so I said, you know what? Give us these needles. Let's see what we can figure out. So, whoops, I took those slides out. I'm sorry. As a reference, though, Bernard Denkena is a fellow with the CIRP from Leibniz, and he had been doing some work on cutting edge geometry and had summarized that. And I had those slides in another talk that I gave, but that's a reference. So if you want to find out some of the kind of state of the art on this, at least as of 2008. Alicona upstairs has got some roundness measurement they're doing, and in the mountains map, you've got some roundness stuff that we've used as well on some things. The measurement of the edge is kind of problematic, and the ones you would really like to measure would be this one and this one, and it's challenging to do that. Some other edges, and if you go to the Olympus website, you can actually see a razor blade that they've measured right on edge. And we were talking with Professor Stemp, and he gave a talk this morning about Mayan bloodletting. And so the question is, can we tell if a stone tool was used for bloodletting? Well, the hypothesis that I've been trying to promote with Professor Stemp that we ought to test is that, yeah, if you're just doing this ceremonially, and maybe even it's a single-use kind of thing, but I come in like this, and it's the edge that's going to have most of the evidence on it. If I'm scraping hides or sawing things and using it until it gets dull, I've probably got a lot of indication on a tool like that. But if it's just like that, it's probably if I'm going to tell anything, it's on the edge. We've got a group here at WPI that's looking at ski edges, and we have a little test too, to test the edge on the ice to see how it's cutting. Cutting tools, of course, it's another application for this edge roundness thing, as well as these biopsy needles. So this is another case of, so why'd you measure it over here? That doesn't have anything to do with how it's cutting. Yeah, but that was where we could measure it, so we measured it there. So the guy that lost his keys, and the policeman finds him at night, and he's looking around, and the policeman, he's under a street light looking around, and the policeman says, "What are you looking for?" He says, "I lost my keys." And the policeman says, "Oh, let me see if I can help you find them." And so the policeman's looking around under the light, and after a little while, the policeman thinks he's looked everywhere, and he goes, "I don't see your keys here anywhere. Are you sure you lost them?" He goes, "No, I lost them over there." "Why aren't you looking over there?" "Well, the light's over here." And so often that's what we're doing in science. Why didn't you measure it there? Well, why didn't you do the calculation of the edge there? Well, we couldn't measure it there, so we did it. We measured it there. So So we sort of lowered our expectations and we said, well, this might not correlate very well with the cutting stuff, but we'll see if we can do roundness measurements anyway, or some kind of radius or curvature. So we looked to see what was available here, and then and we'd like to note right up front that the existing sort of conventional scale decompositions might not be the most suitable for this particular application. So we measured them on the Lext, and this was a tricky kind of thing. Here you can see the needle there. So you particularly don't want to poke your objective with this thing. And so the best we could end up with on the measurement was something like this. And so this is the middle of the needle. We don't expect anything there. And then the edge that we would really like was over there, and we just couldn't get to it without cutting up the needle. So we satisfied ourselves with this edge so we could get on with the work. And there it's shown, with the whole thing and the confocal thing, and there's the height map there. And what we did was we averaged a bunch of profiles along the edge. We didn't have to do that. We could have done one at a time too. So this part out here is the part that was not measured, and then here's the measured part. So here's the shaft of the needle, and this is coming around this rounded part. So we haven't got very far into the straight, through the wall. So we're going from the exterior of the shaft around the edge, and we're not really getting onto this wall at all here, because this goes around and would have to end up going down this way somehow, parallel to this, right? So it would be hard to measure anyway. All right, so the radius calculation, so we've since started calling this curvature. Now this is, so we looked at a number of different ways of doing this, and this is one of the ways we ended up using. So it's called Herons method. So we take these 3 points, and there's A, B, and C. Right, so C is the long side, A, B are the two short sides. And then you calculate S and you calculate K from A, B, and C, and then plug it into this equation and calculate R. Now obviously we could have just as well as, and then R, I'm sorry, you don't calculate. No, I'm sorry, here's where we calculate the radius. Okay, so here's K there, and we've got A, B, and C, and we use S to calculate K. I'm sorry. All right, so S goes in there, and K and A, B, and C. Anyway, this is Heron's method. Heron developed this before Pythagoras got to work sometime, and it's based on what circle fits to these points, and it works well as long as all 3 of these are on the same side of the circle. In other words, the C is across the diameter, and they're all on the same side. I mean, the limit would be, and I'm trying to see where the diameter is here, but the limit would be when C spans the diameter, and so the middle point is kind of in the middle of one side. As soon as it starts to get even more pointy, this doesn't work. Anyway, so positive, we take the normal sign here where this is positive, and that would be a negative. All right, so what we're doing is we're taking this method and sweeping it along the profile. So here's the profile, and so the distance, let me get back to this. The distance, our scale here, is the distance here, C. So we pick 3 points, but 1, 2, 3, and then we've got line segments A and B, and so we just plug in and do the calculations. All right, so now the distance C is 2.5. Well, 2.5 is actually in our sampling direction, so that defines the scale. So here's the profile, and here are all the curvatures, or 1 over the radii. So out here in this mess, we've got a mess, right, and that doesn't really mean anything. And then we've got this, because that's unmeasured. But then we've got, here's the radius at this scale as a function of position. So to my knowledge, it's the first time anybody's calculated this long a profile. And then something funny here happens at the end. And we can see there's two little kinks in this, and we can see those changes right there. There's the radius that goes along with that. Go to a slightly larger scale, and notice these numbers here. So we're getting the biggest curvatures at the finest scales, which is, so that's like 0.2. This is now like 0.02, so watch out for the auto scaling. And so then we've got, here we can again trace these two changes in curvature. This is now 12.5 compared to 2.5. So we're on quite a larger scale, and that little line represents the scale. And then here, let's go to an even larger one. And at this larger scale, we don't even find these two things. You know, and and then we've got this junk out here, which is relatively flat. And that's what we're seeing here, is that this has a curvature near 0, as we would expect. And then, so here's the longest scale, 105, and you'll notice too that we can't get to the ends with this, obviously, because we start at one end, and the first curvature that we can calculate is half of this length. So if we look at this, you know, we're starting right about 50, which is what makes sense. All right, so now this increments number, we're going to go through a series of these. So this increments number is the number of sampling intervals that we're going through. And then, and this is the position, the midpoint x-coordinate along the profile. So here's position, and here's scale. All right, so the contention is, and we've got, this is slightly different, because we were looking at relative area, relative length, and sort of volume or filling volume as a function of scale, but not as position. Now, obviously, we could have looked at these things as functions of position. Slope would make more sense to look at it perhaps as a function of position and scale. So we could do the same sort of thing. And in fact, if we look at calculus, we do a double derivative of the slope. It's like the curvature, but there's some nuances there that we've been working on as well. Anyway, so this is the first time we're looking at this as a function of position. So it's easy to get confused and think we're looking at a profile, but here's the position on the profile, there's the scale and increments, and here is 1 over the radius, or the curvature. Right? And so this is the noisy part of the unmeasured points. It's all over the place. And here are the measured ones, kind of falling into some typical, you know, increments of the radius, which has to do, I think, with, you know, that we're right at the sampling interval. All right, so watch this and watch what happens. We'll go through this. All right, whoops, I overshot. So and the other way to tell where we are on the scales, we see we don't get to the ends anymore. So these were these two little bumps, remember? And we can start to see, oh, that disappeared. And so we're not using the auto scaling, the curvature's staying the same. So not surprisingly, the bigger the scale, the more we start to concentrate on the middle of the profile and towards a 0 radius, because we're looking at such a long thing. Okay.
So increments are just proportional to your length scale?
Yeah. And this, the reason we're doing increments here instead of some sort of length scale or something is because I didn't catch Matt while he was programming this to say, Matt, nobody's going to know what increments are. I'm going to have to explain this every time I show this. Can you change that? And he didn't change it. So.
And increments 1 is so messy because it's essentially sampling length. This
is the sampling interval, right?
So you really need a length scale of 2 sampling intervals before you can get
Oh, yeah, right.
It makes sense.
And yeah, that's a good question. So it's.
So 1 kind of will just give you a jump.
I think 1 is right. Now you need 3 points in order to calculate this. So the minimum increment is 2 sampling intervals if you're looking at C. Yeah, no, that's right. And I should have had him just straighten this out. But the exciting thing was, Matt's really good at this, and sometimes you work with undergraduates and they're there, you know, pretty consistently. And then sometimes they think, oh, this would be fun to work in the lab, and they do it once or twice, and you never see him again. So Matt was coming back again and again, and he was good at it. But he was also involved in so many other things on campus. So we go down to present this to ASPE in Charlotte. And I go, Matt, we need a couple more slides. Yeah, I'm getting to it. You know, I was working in the robotics contest last week, and I go, Matt, we still need some more slides. Matt, it's lunchtime. We're doing the second presentation after lunch. We need the slides. Yeah, it's almost done. It's almost done. Matt, I don't want to miss the first presentation after lunch. I'm doing the second one. Can you get the slides done? Yeah, they'll be ready. They'll be ready. So, as I'm stepping up to the podium, he hands me the presentation with the last two slides. Matt, you really should have seen the other presentation. Yeah, I know. I had to get the last two slides. So that's why it's still increments. But anyway. Boop. All right, so here's this issue with, you know, what's the smallest radius we can calculate using Heron's method and with the scale. And so there's the minimum possible radius, and there's the radius that we actually calculated. So the issue actually is we need a better way of doing that, and that comes from the calculus, and I'm not sure I have a slide on that. Here's another profile just to show another one. So lots of times we're right on this minimum, which means that C, you know, the two furthest apart points are on the diameter of the circle. And if they, you know, sort of move below the diameter, then I'm actually looking for a radius that's smaller than the circle, because Heron's method fits the circle, right? And I'd like all 3 points on the same half, and then I think, yeah, I've got a radius that's kind of like what must be there. But if 2 points are on one half, the other points, you know, it doesn't work out so well. So that was our first attempt at that. Here's another example of that. So this is an edge on a piece of aluminum, 6061 T6. And so this was honed. Actually, when we look at the machine stuff on edge, this is measured with the Olympus. So it does a nice job of measuring edges. The razor blade's really tricky. We tried that, and I asked them, the one on their website, they had to fuss with a little bit. But I think that does a very good job of measuring that edge, getting all the detail on the edge. Then we put this in a mass finishing machine and tumbled it for different amounts of time. The mass finishing machine's a Bel Air finishing machine that's made by one of our alumni. And you can see, this is neat about, you know, how the edge changes as a function of time in there. And so, you know, as you're looking at mass finishing for taking off burrs and, you know, rounding things, quantitatively, how is this working? So the mass finishing machine, for those of you who are not familiar with it, is like a washing machine, kind of jiggles the parts around somehow by turning or doing something, or you can take a robot and drag them around with abrasive media in it. And you use all kinds of funny things for the abrasive media. You can use rice husks with, you know, diamond dust or something, and it does it. So it takes the sharp stuff off your part. Most engineers don't know anything about this, and they go and they make their first parts in industry, and then they find out these things can't assemble because they got burrs all over them, and then they go, all right, now what are we going to do? And then they go to the web and they find, oh, I can do this, and so they get to throw them in the mass finishing machine. But so the unfortunate thing if you make mass finishing machines is the guy who's buying it has already spent all of his budget because he didn't know he needed it, right? So this isn't always the best sort of thing to be selling it. Anyway, so here's a picture of this thing. There's all kinds of different abrasives that go in this little penny, and we get some of that. So that's a nice shiny Bel Air mass finishing. So here's here we just showed 3 different scales and what's happening to this. So again, we've got to watch the auto scaling that goes up to 0.4, 0.4, 0.4. We're looking at the curvatures on this. And so as we go to finer and finer scales, we're seeing here the straight sides with 0 curvature, right? So this is 1 over the radius, and there's the curved part, and so we can see how that is, you know, sharper here on this one, and here we're hardly picking up that edge at all as we hop over the thing. And so anyway, curvature is function scale. So the question here is, that we would like to get to is, can we find some functions that seem to work well with the curvature at some particular scale? So we're going to do these ice shaving experiments with a ski edge kind of thing next. But we would be delighted to collaborate with somebody else in doing this. One of the things that Jack Clark, who will be hosting this event next year at CSU but couldn't make it this year, he had started working on some project where, will a cutting tool edge last longer if it's pre-rounded a little bit? And that's a hypothesis, and if we pre-round it in the mass finishing machine. But I'm not sure where that project's going, and we would love to be able to try some characterizations on that. So here at one scale, and this is on a poster upstairs as well, and you can see some of the work in the poster. I think the poster has got an update on the using calculus. There's a formula in calculus for radius. Often we use just the spatial derivative of the slope, so the change of slope with position. That turns out only to work at the finest scales, which isn't so surprising since it's based, we're trying to use a finite difference to approximate a derivative. But if there's an also slightly more complicated function, and if we use that instead of the abbreviated change in slope, we come up with a better estimation of the curvature. And I think finally what we're going to do is use Heron's method for the long ones, and then use the calculus-based methods when we start getting something that we get 2 points on one side of Heron's circle and one on the other. And so when we see that condition, then we'll go to the calculus-based thing, and I think we'll have a good estimation there at all scales that way. So we've looked at length, area, volume, slope, radius, all changing as a function of scale. If these things are in your model, when you're trying to model what a surface is doing or how the surface is forming, and you don't have scale in there, then you're obviously missing an important part of this. So, and then we find that correlations, ability to discriminate, are improved if we search in the scale space, or spatial frequency or wavelength, whatever you like to call it. So as you said, let's get the right geometric feature at the right scale. Although it seems like if you get the right scale, in some cases you don't have to be so picky about the geometric feature. So, thanks for your attention. So we've got a little bit of time. I'm sure there's coffee up